Welcome, students, to your first instructional video of the school year. We have Vivaldi's Four Seasons in the background tonight, and we're talking about the real number system. So let's jump right in and get started with our video. How do we categorize numbers? Well, there's several different ways that we categorize numbers that you already know about. Odd and even, okay, which actually looks like, there we go. Odd and even. And how about prime and composite? And the main one that we're going to be looking at half of, real and complex. And complex numbers are also imaginary. And you learn about those in Algebra 2. Imaginary. All right, so the reason that we organize numbers, or that we categorize numbers, I should say, this way, is because these different categories have different characteristics. One of the cool things about higher level math is you start talking about stuff that's a really simple concept that you can apply to really difficult problems. Even numbers are always in the form 2 times n, and odd numbers are in the form 2 times n plus 1. You can actually do a bunch of different cool things with that information in a course called discrete math or number theory. And it's all about how evens come in. Everything in an even, it comes in pairs. You could split into pairs. And in an odd, you could split into pairs, plus 1 left over. Prime and composite numbers are important because a prime number can only be arranged in one way. So if you have, for example, you used to do arrays back when, go back to third grade, think third grade math. If we had 3 times 5, we'd have an array with 15 objects in it, 3 by 5. So 3 by 5, right? 3 by 5. But if I said, here, take 17 objects and arrange them in an array, the only way you could do it would be 1 by 17, like that. Real and complex numbers. Well, you're not going to worry about complex numbers. We learn about those in Algebra 2, but we're going to talk about the real number system. And it's it's kind of literally what you see in the names. Real numbers are real, complex numbers are complex. So real numbers can apply to things. Complex numbers really can't. Something you'll learn about in Algebra 2. Okay? Here is the organization of the sets of real numbers. This is a Venn diagram, and John Venn designed the Venn diagram. It's not just your traditional compare and contrast. It shows a relationship between parts. In the Venn diagram, one category fits inside the next. So you have here 1, 2, 3, 4, 5 categories of numbers within the real number system. So you have your natural numbers, that's your counting numbers, your whole numbers, include your natural numbers. Your integers include your natural and your whole numbers. Your rational numbers include all of those. And then the opposite of rational is irrational. And altogether that makes up the real numbers. Let's define each one. Take your time, pause it if you need to, but do make sure you listen to the definitions in addition to just writing. We start with our natural or counting numbers. That's the whole numbers from 1 upward. So 1, 2, there we go, 3, 4, and so on. Ellipsis. Whole numbers, 0 in the natural numbers, which I've always joked would be like totally the name of my band, if I ever had one. 0 in the natural numbers. So it's 0, 1, 2, 3, 4, and so on and so on. Integers, the whole numbers and their opposites. So that's 0 in the middle, counting up. And so keep going above 4, and then counting backwards as well. Negatives. Negatives have lots and lots and lots of real-world applications. A sad one being debt, for example, but we'll talk about more of those in a minute. Rational numbers. Well, in a rational number, those are numbers that can be written as fractions, can be written in fraction form. So, your terminating decimals, 0.6, because that's 6/10. Your repeating decimals, 0.2 repeating, for example, is a fraction. You can take your repeating decimals, put the digit that repeats over 9, that's 2/9. So 0.6 would be 6/10 or 3/5. So these are all numbers that you can definitely express as fractions. How about negative 1.7? I can express that as a fraction. That'd be negative 17/10. And I can express all of these numbers above as fractions. I can express 0 as a fraction. It looks a little awkward, but 0 over 1 I mean, you could do that. It doesn't change the value. 1 over 1, 2 over 1, 3 over 1, 8 over 2. I mean, you can write any of these numbers up here as fractions. And that's what we were referring to in our Venn diagram on the previous slide, that one category fits in the next. Your irrational numbers are completely different from the other numbers you see up here. They're non-repeating, non-terminating decimals. They don't repeat, so there's no pattern in the decimal values, the numbers that come after that decimal point, and they don't end. They keep going on forever and ever and ever with no specific discernible pattern. And these are numbers that cannot be written in fraction form, and we'll examine some more examples of those in a moment. Another way to organize your thoughts about the real number system is with a tree map. So you have your real numbers up top. We already established that you split into, there we go, the irrational and the rational numbers. Then the rational numbers are your numbers that can be expressed as fractions, irrational or not. Well then, as you go down the tree map, it's like you're organizing it the opposite way in your mind. It's going the opposite direction. Your categories, instead of getting broader, the way they did in the Venn diagram, they're getting smaller. They're getting less broad. They're getting more specific. So you got your rational numbers that can be expressed as fractions. Take out anything with a decimal part in it, and you're left with your integers. Now notice that means that rational numbers can be both positive and negative. Okay, so can integers, but not whole numbers. Whole numbers start with 0 and work our way up. So now you take out the negatives from the integers and you got your whole numbers. Take out the 0 and you've got your natural numbers, 1, 2, 3, and so on. Now, irrational numbers we should talk a little bit more about. They totally confounded the early mathematicians. In fact, I think there was a myth I remember, well, I don't know if it's a myth, but a story I remember reading about Pythagoras. And we'll learn more with the Pythagorean theorem later in the year. But Pythagoras was a very, very important mathematician. The legend, or the history says that he killed a guy to prevent the rest of the academics from finding out about numbers like the square root of 2. It's a crazy story, but I think true. Anyway, irrational numbers, so they include values like pi. Now pi you know of as 22/7 or 3.14159, and so on and so on. It's not a terminating decimal, it's not a repeating decimal, but there's no pattern to it. So that's pi. These weird decimals that have these weird patterns, like this one, would be an irrational number. And then it includes square roots of non-perfect squares. So I'm going to give you some examples of numbers in a moment, but we can say the square root of 2, for example, is an irrational number. The square root of 5 is an irrational number because they're not perfect squares. Not the square root of 9, though. Because when we say square root, and we'll get to that definition in just a second, what are we asking about? So that's not an irrational number. So perfect squares and square roots. So what are we talking about here? The trouble with defining this stuff is that you have to really tie knots in your tongue getting the definition together, because it sounds very strange. You have to keep using the same words over and over, kind of referring to different things. But bear with me, let's read it. A perfect square is a whole number whose square root is a whole number. I'm going to ask you to know the perfect squares from 1 to 400, and we're going to list them in just a second. So a perfect square is a whole number whose square root is a whole number. So that when you look for the number times itself that gives you that value, if it's a whole number, that's a perfect square. Perfect squares from 1 to 400, we've got 1 squared is 1, 2 squared is 4, 3 squared is 9, 4 squared 16, 5 squared 25, 6 squared 36, 7 squared 49, 8 squared 64, I faltered for a second, 9 squared 81, 10 squared 100, 11 squared 121, 13 squared is 169, 14 squared is 196, 15 squared is 225, 16 squared is 256, 17 squared is 289, oh, I'm on a roll, I can do this, 18 squared is 376, uh-oh, I don't know 19 squared, I don't know 19 squared. Well, let's talk about what the square root of a number is while I check what 19 squared is. I almost made it. Didn't quite make it, though. So I'm going to use my quick calculator here. 361. Oh, well, then this is wrong. 324. That's 18 squared. And then 361. So, hey, I caught my own mistake. All right, so the square root of a number is the value that, when multiplied by itself, gives you that number. And that's the definition that always bothers me. So the square root of a number is the value that when you multiply it by itself, it gives you that number. So the square root of 9 is, what times itself is 9? Yeah, 3. But I want you to recognize something here. You have actually two square roots of the number 9. There's two numbers that you can multiply and get the number 3. You can multiply the number -3 by itself and get 9, or you can multiply the number 3 by itself and get 9. So you have both a positive and a negative square root. The positive is called the principal. This is the principal square root, P-L-E at the end, not P-A-L. P-A-L will be, that'll be Dr. Crum. So the principal square root right here, and this is the negative square root right here. All right, the square root of a non-perfect square number is an irrational number. I keep repeating that because that's one of those things we really have to make sure we get. Okay, I'm going to finish this off. I'm going to give you a list of numbers, and I want you to locate them on this number line. So I'm going to actually pause my video, write them all in, and then I want you to just have at it and stick them on this number line here. And then we'll also talk about where they are on the real number system. Okay, and we're back to it. And I have a very naughty kitten sitting next to me who keeps trying to knock the stylus out of my hand. It's possible you may end up being able to hear her purr on the video, because she is right next to me. And she is a wild thing. Anyway, okay, so numbers. So we've got 1/4, 0, 1, -6, -3, the square root of 4, negative square root of 25, pi, square root of 26, -7.5, 0.2 repeating, and 5. Square root of 5, excuse me. And we're going to locate all these numbers. So let's start with the easy ones. We definitely know where 0 is. I'll use blue. So there's 0. All right, so we got 0. 1, there's 1 right there. So we got 1, easy peasy. See anything else? You know, -3, -6. That's easy because they're easy to find. -3, -6. Got it. What about the square root of 4? Well, what is the square root of 4 equal to? Well, the square root of 4 is equal to 2. So the square root of 4 is going to be right here. Now, if you even want to get specific for what we just learned, you could also say the square root of 4 is over here at -2. But since there's nothing in front of that square root of 4, we only give the principal square root. What else do we have? Well, we've got negative, look at that one, negative square root of 25. So that's -5. -5. So we got that one. All right. -7.5. We can put that. That's going to be halfway between -7 and -8. 1/4. 1/4 is going to be really close to 0 on this because it's such small unit. So 1/4 of the way from 0 to 1. So that's 1/4. That starts to get a little more complicated. Now, 0.2 repeating, we said, remember, 0.2 repeating, that's 2/9. So 2/9 is going to be, pretty much the same place as that 1/4 is, only because we can't show anything in between there. Our line plot is not quite specific enough. What about the square root of 5? Where am I going to find that? So let's look at that. The square root of 5. Well, it's going to be between the square root of 4 and the next perfect square, which is square root of 9. That's where that's going to be. So it's going to be between 2 and 3. And that's how you locate a square root. You find the two perfect squares that are on either side of that number inside the radical, and that's where this number, the square root of 5, is going to be, between the square root of 4 and the square root of 9. Which one's it going to be closer to? Well, is 5 closer to 4, or is 5 closer to 9? 5 is closer to 4. So we definitely say that it's closer to 2. So closer to 2 than 3. And the last one is the square root of 26. So do the same thing. Well, 25 is there. And then the next one after that's 36. So the square root of 26 must be between 5 and 6. Much, much closer to 5. And I'm going to go ahead and stop there because we've reached our limit for the length of time for the videos. Hope you enjoyed it. If you have any questions, jot them down at the end of your notes, and I'll see you guys in class.